Okay, question number 42. A parachutist bails out from a helicopter at time t equals 0. After a certain time, he opens his parachute and then reaches the ground. Which of the following graphs best represents the variation of the vertical component of the velocity v of the parachutist with time t? This is what happens. Now the parachutist, he gets off the helicopter, and then till he attains the terminal velocity vt, he doesn't open the parachute. After attaining his terminal velocity, that means a constant velocity, what he does is he opens the parachute. Then what happens? When he opens the parachute, what happens is the drag force, F drag, okay, the resistive force from the air, it increases. You know by experience, then what happens? Then what happens is the upward force increases, and then eventually it's a deceleration downwards. Earlier it was an acceleration downwards, but now it becomes a deceleration downwards, right? So then you have to consider that idea, and eventually he comes to the floor, and then he comes to the floor with a certain velocity v, right? Now listen, here's the graph. What happens first is, now when he steps out of the helicopter, he experiences a drag force. That's obvious, but his weight is acting downwards, therefore there's a resultant acceleration downwards. But as he moves down with the velocity v, because drag force increases with the velocity, right? The drag force that's acting on an object increases with the velocity. Then now he's going under gravity, but upwards drag force acts. When the drag force acts upwards, the resultant acceleration downwards decreases. Then, but though the acceleration decreases, the velocity keeps on increasing because there's a positive acceleration downwards, right? Now there's an acceleration downwards. There is an acceleration downwards. It may be decreasing, but it is accelerating downwards, right? The acceleration may be decreasing, but it's accelerating downwards. If it's accelerating downwards, velocity has to increase. But how does it increase? Reluctantly, because the acceleration is showing discouragement increase. It's decreasing because the drag force keeps on increasing upwards, then the acceleration is decreasing. Then the VT graph should show that gradient is decreasing. Yeah, you can see that it kind of attains the terminal velocity, right? The gradient is decreasing. Now, why is the gradient decreasing? Because the acceleration is decreasing. Because of a VT graph, the gradient gives you the acceleration, right? What happens after this point is something different. I'm opening up the parachute. Then the drag force increases a lot. Then the resultant force is upwards, right? Resultant force is upwards. Then what happens is that there is deceleration downwards. Then what happens is the velocity downwards decreases. The velocity downwards decreases. Now the velocity decreases. Therefore, the drag force decreases. You see? When the velocity downwards decreases, the drag force decreases. Isn't that funny? So then what happens is, again, though the velocity decreases, the gradient should decrease. So I can't have a gradient like this. But eventually what happens is it comes to a certain velocity and he comes to the ground. Right? Yeah, that's the idea. So then we have question number 43. Question number 43. Consider the following statements about half-life, T-half, of radioactive atoms in a sample. Statement A. T-half changes with the number of radioactive atoms present in the sample. Wrong. It doesn't depend on the number of radioactive atoms present in the sample. Now, if I start with n number of radioactive atoms, it becomes n over 2. This is called T-half. When the initial number of radioactive atoms becomes half of its number, then it is T-half. What is T-half? It's the time taken for n to become n over 2, for the number of radioactive atoms to become half of its number. Then it's the same when n over 2 becomes n over 4, right? So it doesn't depend on the number of radioactive atoms present in the sample. Second statement, T half changes with the date and the time of the prepared sample. No, there's no relationship at all between the date and the time of the prepared sample. That's like hilarious, right? The statement itself. Statement C, T half does not change even if the radioactive atoms are ionized. Yeah, ionization the ionization doesn't have anything to do with this radioactivity, right? Ionization deals with removing electrons and stuff, right? But we are dealing with the nucleus. We are not dealing with electrons. Therefore, T half is the time taken for the initial number of radioactive atoms to become half of its number. We are not talking about ionization here. It's different. Therefore, T half does not change even if the radioactive atoms are ionized is correct. So statement C is only correct. Right, 44th.